For 3,000 years, humanity has been waging a silent war against the most violent force on Earth. Not armies, not storms, the ground itself. Every fault line was a sentence. Every tectonic shift was a verdict. And civilizations built their greatest achievements directly on top of the threat. From the swaying pagodas of ancient Japan to the reinforced walls of the Inca Empire in Peru, our ancestors discovered structural secrets that modern science is only now beginning to fully understand. These primitive builders survived catastrophes that would level a modern city. How? The answer isn't luck. It isn't myth. It's 3,000 years of accumulated genius, hidden in wood, compressed into earth, and carved into stone. Get ready to uncover the greatest engineering secret ever buried beneath our feet. What actually keeps a building standing when the ground beneath it moves like a wave? The answer isn't thicker walls. It isn't deeper foundations. The answer is a principle so counterintuitive it took humanity 3,000 years to fully grasp. Flexibility beats rigidity every time. When seismic energy slams into a structure, that energy has to go somewhere. Rigid buildings resist and shatter. Flexible buildings absorb and survive. We'll decode the hidden mechanics of ancient timber frames, compressed earth walls, and independent central columns. From civilizations that solved structural engineering without a single equation, to artificial intelligence that predicts collapse before a crack appears. Witness 3,000 years in the evolution of the one idea that stands between a city and total destruction. Ancient civilizations built their greatest monuments on the most dangerous ground on Earth. The fault lines of Japan, the tectonic battlefield of the Andes, the seismic corridors of the Mediterranean. They had no seismographs, no structural software, no modern materials science, and yet their buildings are still standing. Thousands of years later, after dozens of catastrophic earthquakes, the walls, temples, and towers of the ancient world remain, while modern concrete structures built last century lie in rubble beside them. This is not coincidence. This is engineering. The story of how humanity learned to live with a planet that never stops moving. A 3,000-year journey from instinct to algorithm, and the structural genius that has always been the difference between survival and collapse. 3,000 years ago, the Earth shook and people died. Buildings collapsed, cities burned, and entire civilizations were erased in minutes. There was no warning, no explanation, no formula, only the survivors, and what they chose to build next. The earliest seismic wisdom wasn't written in books. It was written in rubble. Ancient builders in earthquake-prone regions studied what fell and what didn't. Stone columns that cracked, mud brick walls that pancaked, and occasionally a timber frame structure that swayed, groaned, and stood. The observation was simple but revolutionary. Some materials fight the earthquake, others dance with it. In ancient Japan, temple builders noticed that the tallest timber structures survived while shorter stone ones crumbled. They didn't know why, but they knew it was true. So they built taller in timber. But in the Mediterranean world, Greek and Roman engineers developed thick-walled stone construction that relied on mass for stability. The strategy was the same as the earliest bridge builders: raw weight as a defense. It worked against moderate seismic events, but against a truly violent earthquake, mass became a liability. Heavy stone collapsed with devastating force. The heavier the structure, the deadlier the collapse. The ancient world was running a slow, brutal experiment. Every earthquake was a data point. Every ruin was a lesson. Civilizations that ignored the lesson were erased. Those that paid attention began to develop the first structural intuitions that would, over 3,000 years, evolve into a science. The transition from raw mass to thoughtful observation marks the first chapter of seismic engineering. It wasn't yet a discipline. It wasn't yet a science. But it was the beginning of something humanity desperately needed. The recognition that the Earth moves, and that we must move with it. In the first millennium AD, two civilizations on opposite sides of the planet independently discovered the same profound truth. Flexibility is a weapon. In Japan, Buddhist temple architects developed multi-story pagoda structures that became the most earthquake-resistant buildings in the ancient world. The secret wasn't in the material alone. It was in a specific structural innovation called the Shinbashira, a single independent central column running the full height of the building, attached to nothing, not bolted to the floor, not fixed to the walls, simply standing at the center, free to move. When an earthquake struck, the building swayed in one direction. The Shinbashira, unattached, swayed in the opposite direction. The two movements canceled each other out. It was a tuned mass damper, built without a single equation, 1,000 years before the concept was formally defined. On the other side of the world, the Inca engineers of the Andes developed Taipei, compressed earth construction that absorbed seismic waves rather than resisting them. Thick walls built from layered rammed earth behaved like a viscous material under seismic stress. They didn't crack and shatter like stone. They deformed slightly, distributed the energy through the layers, and held. The Inca also mastered trapezoidal stonework, walls that were wider at the base and narrower at the top, with stones cut at slight inward angles so that seismic motion actually pressed the stones more tightly together, rather than pulling them apart. An earthquake made these walls stronger in the moment it tried to destroy them. Both civilizations, Japanese and Inca, arrived at the same conclusion through entirely different methods. The goal is not to stop the earthquake. The goal is to manage its energy, absorb it, redirect it, outlast it. This fundamental strategic shift, from rigid resistance to calculated flexibility, is the most important idea in the entire history of seismic engineering. Everything that came after, every damper, every isolator, every smart sensor, is a refinement of this single ancient insight. In the second half of the 20th century, seismic engineering transformed from a reactive discipline into a predictive science. The key breakthrough was a concept that would have been immediately recognized by any Inca engineer. Separate the building from the ground. Base isolation. In a base-isolated structure, the building sits on a system of layered rubber and lead bearings. When the ground moves during an earthquake, the isolation system absorbs and dissipates the energy before it reaches the structure above. The building moves, but far less than the ground beneath it. The isolation layer does what Taipei walls did in the Andes. It acts as a buffer between destructive energy and the structure it threatens. The first modern base isolated building was completed in New Zealand in 1981. Within 2 decades, the technology had spread to hospitals, government buildings, and critical infrastructure across Japan, the United States, and beyond. The second major innovation was the tuned mass damper. A large mass, sometimes hundreds of tons of steel or concrete, suspended inside the upper floors of a tall building. When wind or seismic energy sets the building swaying, the damper swings in the opposite direction, counteracting the motion. Taipei 101 houses a 660-ton steel sphere suspended between the 87th and 92nd floors. It is the direct descendant of the Shinbashira column, the same principle, scaled to a skyscraper, calculated to 4 decimal places. The third transformation came from computing. Finite element analysis allowed engineers to model every stress point in a structure under simulated seismic loading. They could test a building against 100 different earthquake scenarios before a single foundation was poured. Design iterations that once took months took hours. Structures that once required conservative overbuilding could be optimized with precision.
The real-world
The gap
result
between
is
ancient
this
intuition
seismically
and modern
isolated
calculation
hospital
was
in
closing.
Tokyo,
And the
standing
results were
calm and
measurable.
protected. The
In the
solutions wie Trotlook
1995
Sovens, the
Kobe
Suaverons can the
base
Thomas just
isolated
with a flowing to the
buildings suffered
cross-grades,
dramatically
and
less
much
damage
in
than
conception
conventional
fashion
structures
syphilis.
beside them. The engineering worked. The shield held. As of 2026, seismic engineering stands at the most remarkable threshold in its 3,000-year history. The buildings going up today don't just resist earthquakes, they think. Carbon fiber reinforced concrete, 5 times lighter than traditional steel reinforcement and completely corrosion resistant, is now embedded with fiber optic sensor networks during construction. Every meter of structure is wired. Temperature, stress, strain, vibration, and micro deformation are measured continuously. Data streams in real time to cloud platforms where machine learning algorithms analyze structural behavior around the clock. The system detects fatigue patterns weeks before a crack becomes visible to the human eye. Maintenance alerts are automatic. Failure predictions are probabilistic. The building knows its own condition better than any inspector ever could. Global seismic retrofitting programs are accelerating. In Istanbul, one of the most seismically vulnerable megacities on Earth, tens of thousands of buildings are being structurally upgraded ahead of the earthquake that geologists say is not a question of if, but when. In Tokyo, In Los Angeles, in Lima, cities are simultaneously building smarter and reinforcing what already stands. Artificial intelligence is now being used to run seismic simulations at a scale previously impossible. An AI system can model an entire city district, thousands of individual structures, varying soil conditions, multiple fault scenarios, and output a detailed vulnerability map in hours. Urban planners use these maps to prioritize retrofitting. Emergency managers use them to pre-position rescue resources. Architects use them to design the next generation of structures from the ground up. The most ambitious frontier is the integration of energy harvesting into seismic design itself. Piezoelectric materials embedded in foundations and structural joints convert seismic vibration, including the constant microtremors that never make the news, into electrical energy. The building doesn't just survive the earthquake, it harvests it. 3,000 years ago, an ancient builder looked at the rubble of a collapsed structure and made a decision. Build differently. That decision, repeated 10,000 times across 10,000 years, is the reason cities still exist on the most dangerous tectonic ground on Earth. We cannot stop the Earth from moving. We never could. But with 3,000 years of accumulated intelligence, from a freestanding column in a Japanese pagoda to an AI running 10 million seismic simulations overnight, we no longer have to fall when it does.